Today we're going to talk about scaling and similar figures. And when we use the word scaling, we're talking about making figures bigger or smaller. As we make those shapes bigger or smaller, we want to make sure that they still seem like the same original shape, but they've just been enlarged or reduced. And so it'll help us to define that term similar figures. Similar figures are the same shape and have the same angles, but all of the sides have been multiplied by a common ratio. And sometimes we use the word scale factor when we talk about that common ratio. So down below I have a red triangle. We're going to say that this is my original shape. And I could scale this shape by making it bigger. And you can see that shape looks the same, right? All the sides are in what we call proportion to each other. They just have gotten bigger overall. So it's still a triangle. The angles of that triangle are still the same, but our side lengths have all increased by the same common ratio or the same scale factor. You're going to notice in this case that in order to make something bigger, my common ratio was greater than 1. I also have an example now to the left that's a smaller example. And this has been shrunk down, or it's been multiplied by a scale factor that is less than 1. In all three of these examples, the shapes should look similar. They should still be triangles. They still should have the same angles, but their side lengths have all changed by the same amount. Now that we understand what similar figures are, let's talk about what we're going to do today. We're going to break today down into 3 different steps. The first step is going to be how we can create similar figures using that common ratio. Again, a common word that we use for common ratio is the word scale factor. So you may hear that term or see that on some of your homework. The second thing that we're going to do after we know how to create those similar figures using the scale factor or common ratio is we're going to determine if two similars that may look alike actually are similar. We're going to do that by using their measurements and see if we actually use that same scale factor to get all of our sides. And then the third part of this video, we are going to find our missing sides or the scale factors of our similar figures. And we might ask ourselves, what was the scale factor for these types of problems? Now, because this video involves 3 parts, you may want to watch part 1 and get some practice with what we're doing on that, and then come back to part 2 and get practice with that. I'll leave that up to you, but we'll go ahead and move on to the first part of this video, which is creating similar figures using that common ratio. So, if we want to create similar figures, we have to start with an original figure. So, I'm going to start with a rectangle here. And I've used grid paper. It makes it pretty easy to do some measuring on this. And so I've got dimensions on this rectangle of 3 units by 7 units. Well, if I wanted to create a similar figure, I need to remember that similar figures have been multiplied by a common ratio. So I could do an example where I multiply by 2. And we know already that that is going to be a bigger example because 2 is greater than 1. Multiplying by greater than 1 makes our shape bigger. So here I've done that. I've multiplied by 2, and that means that I need to multiply all of my sides by 2. So I can take a look there. My side that was 3 should now be 6, and my side that was 7 should now be 14. And that means that those figures are similar. All sides have been multiplied by the same thing. Next, we're going to look at another example. If I multiply by 1/2, a number that's smaller than 1, I should end up with a shape that's smaller than my original shape. We're going to follow the same process. We're going to multiply all of the sides by that common ratio. In this case, it's 1/2. So 3 times 1/2 should give me 1.5. And 7 times 1/2 should give me 3.5. And if you need practice multiplying your fractions, make sure you go back and get some extra practice with that. Let's look at one more example In this case, we're going to look at an example of 1/3. Think to yourself for a minute, is that shape going to be bigger than the original shape or smaller than the original shape? Hopefully you've thought and determined that since it's a fraction, it's going to be smaller than the original shape. Let's take that one step further. Since we know it's going to be smaller, I want you to think if it's going to be smaller than our similar shape that we made that was multiplied by a scale factor of 1/2, or if it's going to be bigger than that shape that was multiplied by 1/2. Well, let's go ahead and take a look, and we're going to see what happens here. You can see that it is indeed smaller, because when I multiply 3 by 1/3, I get 1. And when I multiply 7 by 1/3, I get 2 and 1/3. Again, multiplying by a fraction will make that shape smaller, and the smaller that fraction gets, the smaller that my shape will get. And since 1/3 is smaller than 1/2, we know that our shape is going to continue to get smaller. That's the basic idea of how you create similar figures. If you're feeling ready, let's move on to the second part of this video. We want to determine if figures are actually similar figures to each other. We can do that in a couple of different ways, but the first thing I want to tell you is you've got to be really careful and make sure that you're not doing this just based on how the figures look. So let's start with the same example that we had in our last case. We had something that was 3 by 7, and I'm going to take a look at a shape over here, and those shapes look pretty similar. They are still rectangles. They look like they have the same angles. They look like they might have even increased by the same amount. But we can't do this based just on how they look. We have to do this based on what was the scale factor, and were all sides multiplied by that same common ratio or scale factor. So let's go ahead and see what happened on this particular shape. We started with a side of 3, and we ended up with a side of 6. So what did I multiply by? Well, I multiplied by 2. So 3 times 2 equals 6. Well, that's pretty simple. So in order for these shapes to be similar, that means that I would have needed to multiply all sides by 2. So 7 times 2 equals 12. Well, wait a minute. 7 times 2 doesn't equal 12. So if that happens, then that tells me that these shapes were not similar shapes. And again, it's really important that you're basing this on the scale factor or the common ratio and not just how those shapes looked, because originally those shapes looked pretty similar to each other. Let's take a look at another example, and this one's going to be a little bit trickier. What do you think about this shape? Do you think that it's a similar shape or not a similar shape? We can see they're both rectangles, but it doesn't really seem like the top is long on the second shape, and the sides are not so short on the second shape, and that's what it looked like on our original. Well, one thing to remember, we have to base this on our measurements and not based on how it looks. And since we know that shapes can rotate and spin around and flip upside down and all that stuff, we might have to think about which sides to this correspond with each other. So if I look at my side 3 and I look at this top side, I might recognize that those correspond with each other. So my first thought might be thinking, well, what did I multiply to get 3 to equal that measurement of 4.5? I also end up with a side of 10.5. And again, I might be thinking, well, maybe this shape rotated. So what did I multiply 7 by to get 10.5? So our process is to go 3 times x, or 3 times our scale factor, it's an unknown value right now, would equal 4.5. And 7 times y, which is also an unknown value, is equal to 10.5. And what we're checking for right now is, was my value of x and y, what I multiplied both sides by, the same? If they are the same, then we know that they are similar. If they're not the same, then we've found out that they're not similar shapes. Well, we might need to do a little bit of thinking to figure out what I multiplied 3 by to get 4.5. Remember, we can work backwards. We can use the inverse operation. and I can start working backwards on this equation. So instead of starting with 3 and timesing it by a bunch of random numbers, I can start with my answer, which was 4.5, and I can work backwards and divide that by 3. 4.5 divided by 3 has to equal my x according to my order of or my inverse operations. So in this case, 4.5 divided by 3 was equal to x, which was 1.5. Let's go ahead and do that same process with our 10.5 value. So 10.5 divided by 7 would equal y, and 10.5 divided by 7 was equal to 1.5. You're going to notice here that, hey, the x and the y value were both the same value. If that's true, then we know that we have created similar figures because the scale factor was the same. One quick note about this is, depending on the type of shape that you have, you need to make sure that that's true for all of the sides. In this case, this is a rectangle, and we know that opposite sides are the same, or they're congruent, they're the same measurements. So we only need to measure 2 sides of this. But if this were something like a pentagon that has 5 sides, or maybe a hexagon that has 6 sides, we'd actually need to make sure we're measuring all of those sides to make sure that this is true. That's the second part of this, figuring out if figures are similar to each other. When you're feeling ready, go ahead and move on to the third part of this video. Here we are in the third part of this video, which is helping us find missing side lengths and scale factor. We're going to use a triangle this time, and this time I have a triangle that measures 8 units on one side and 4 units on the other side. Now, for this example, we're not actually going to use that third side because it's really hard to measure because we're cutting through parts of our units there. But just for the sake of example here, the actual measurement of that side would be around 8.94. We can learn some other ways to calculate that, and that will be some stuff that you do next year in Math 7-8. But anyways, for now, we're going to focus on just our 2 sides, our side 8 and our side 4. Well, let's go ahead and see if we can find some missing lengths and scale factors. If we are given another triangle and we are told that this triangle is similar to our original triangle, well, we should be able to do some work to find missing side lengths and scale factors. So I'm given a little bit more information here. I know that one side was a value of 2 and one side is missing. It's a value of x. Well, the first thing that I need to do is I need to determine my scale factor. And in order to determine my scale factor, I'm going to think about, well, what is scale factor? Well, it is a number that I'm multiplying one side by to get the other side. So 8 times something, it's unknown right now, has to equal 2. If that's true and these shapes are similar, then I can apply that down below as well. 4 times something, that's going to be my scale factor, has to equal that missing value that's x. Well, if I'm not quite sure what I can multiply 8 by 2 by, remember, we can work backwards. So let's go ahead and work backwards. 2 divided by 8 is going to equal that question mark, and 2 divided by 8 is simply 1/4. Well, that means that 1/4 is that question mark, and I can now fill that in my second equation. We've found our scale factor, now we can find our missing side. 4 times my value of 1/4, which was my scale factor, has to equal x, and 4 times 1/4 is equal to 1. So that tells me that my missing side of that triangle was 1. There's a few examples with how to work with scale factor. Since this video is kind of long, again, if you've broken it into 3 parts, you might want to go back and practice each part individually. Please let me know if you have questions, and as always, good luck.